Hello everyone. Today I'm going to give you a tip that will help you a great deal in stoichiometry. Here is a question that you might see on a stoichiometry exam. So you are given a reaction between ammonia, which is NH3, and copper oxide, and it produces nitrogen, copper, and water. We are told that there are 3.5 moles of copper oxide and 2.3 moles of ammonia. Find NH2O. N bracket notation, like a function notation almost, is the number of moles of. So N of H2O is the number of moles of H2O. Let's write down the information that we already have. The number of moles of copper oxide is 3.5 moles, and the number of moles of NH3 is 2.3 moles. And we have to find the number of moles of water, H2O. Before we can do this, we need to find the number of moles of reaction. So I'm going to think of how many moles of reactions take place. This is the number of moles of reaction, N arrow. Let's think about what it means. When you have 2 molecules of ammonia, you get 1 reaction. When you have 4 molecules of ammonia, you get 2 reactions. When you have 6 molecules of ammonia, you get 3 reactions. You get the idea. The number of moles of reaction would be equal to the number of moles of ammonia divided by 2. How about the number of moles of copper oxide? How can we write the number of moles of reaction from the number of moles of copper oxide? If we have 3 formula units of copper oxide, then we get 1 reaction. If we have 6 formula units of copper oxide, then we have 2 reactions. If we have 9 units, then we have 3. The number of reactions that can take place is the number of units divided by 3. Notice that the 2 that is dividing the number of moles of ammonia is the same 2 that is the coefficient of ammonia in the stoichiometric equation. Notice also that the 3 from the copper oxide in the stoichiometric equation is also the same 3 here. That is divided by to obtain the number of moles of reaction. This should be quite intuitive, because if there are 3 of these needed for 1 reaction, then the number of reactions is going to be the number of these things divided by 3. It makes intuitive sense. In fact, this is not only true for the reactants, but also for the products. And this realization that the coefficient of a substance on the stoichiometric equation is also the denominator in this equation, which relates the substance to the number of moles of reaction, is the key insight which I want you guys to take from this video. This one insight, even though it might seem simple now, will help you a great deal. So now we know how to find the number of moles of reaction. So what? How will this help? Well, first we need to see if there is a limiting or excess reagent. Remember that we always use the limiting reagent to find the number of moles, because the limiting reagent limits the number of reactions that we can have. So let's try and find the number of moles of reaction if the limiting reagent was copper oxide. The number of moles of reaction that would take place if there were 3.5 moles of copper oxide as a limiting reagent, which means that all other reagents, that is ammonia, was in excess, would be, from this equation, the number of moles of copper oxide, so 3.5, divided by 3. 3.5 divided by 3. 1.167, or I'm going to round to 3 significant figures, so 1.17. This is the number of moles of reaction that would take place if copper oxide was the limiting reagent. Now let's consider the case where ammonia is the limiting reagent. How many moles of reaction would take place if ammonia was the limiting reagent? To find the number of moles of reaction, we need to divide the number of moles of ammonia, which is 2.3, by 2, the stoichiometric equation coefficient. 2.3 divided by 2. Here we can see that we would get 1.15 moles of reaction if we had only 2.3 moles of ammonia that was a limiting reagent. Looking at both of these, we can see that clearly ammonia, being the limiting reagent, would give us less moles of reaction. Now remember, limiting means less. So the limiting reagent is the one which has less moles of reaction. This is the one which prevents there from being more reaction. If there was more of this, there would be more reaction. So which of these two values is less? Obviously, it's the 1.15 value. And so ammonia, which is the one which gives this value, would be the limiting reagent, because if ammonia is the limiting reagent, then less moles of reaction happen than if copper oxide is the limiting reagent. So the reaction will stop after 1.15 moles of reaction have happened, and it won't go to 1.17 moles because there won't be enough ammonia to sustain the reaction. So now that we know the limiting reagent and the number of moles of reaction, we can rearrange this equation to find the number of moles of water from the number of moles of reaction. So the number of moles of reaction is equal to the number of moles of water divided by 3. Therefore, we can rewrite this equation to solve for the number of moles of water. In this question, the number of moles of water is all that we're interested in. So I've isolated water and the number of moles of reaction into this one simple equation from the equations above. Now we can simply rearrange this by multiplying both sides by 3 to get the number of moles of water is equal to the number of moles of reaction multiplied by 3, as shown here. So we know that the number of moles of water is equal to the number of moles of reaction multiplied by 3, and we also know that 1.15 moles of reaction take place. Therefore, we can calculate the number of moles of water that are produced from this reaction by multiplying 1.15 by 3. .45 moles of water are produced from this reaction. Now this process may seem long now, but trust me, it's a very fast process once you get used to it, and it makes intuitive sense if you think about it. So the number of moles of water is 3.45 moles. Now suppose that you were given the fact that NH3 is the limiting reagent in the beginning, and you weren't given the number of moles of copper oxide at all. How could you find the moles of water in a faster manner? This type of question is very common in combustion reactions because oxygen is always in excess, except for in very specific situations. Whenever you're having a combustion reaction in open air, oxygen is in excess, and so the fuel is the limiting reagent. So in such a type of reaction, or in any type of reaction where you know the limiting reagent, there is a faster way in which you can find the number of moles of a reactant or product. Here I have changed the original question so that you're only given the number of moles of ammonia and the copper oxide is assumed to be in excess, and you're asked to find the number of moles of water. How can you solve this equation simply and easily? Many people get confused with ratios, but there is a very simple way using the same central idea of the number of moles of reaction in which you can find this effectively every single time. And that involves this ratio which I had explained previously. So we already know that the number of moles of reaction is equal to whatever reactant or product it is present in the stoichiometric equation divided by its coefficient in the stoichiometric equation. So in this example, the number of moles of NH3 divided by 2, or the number of moles of copper oxide divided by 3, and so on. Now, in this equation, in this kind of situation where you don't need to find the limiting reagent, it's already given to you, you can take a shortcut using this very method. This might be quite simple once you figure it out. So what you do is you again focus on the parts that are relevant to you and ignore the rest. So you're given the number of moles of NH3, so you take that part of the equation, and the 2. Remember, the coefficient is important, the denominator, which was the coefficient from the stoichiometric equation. And then you take this part, the moles you want to find, NH2O, and you divide it again by the stoichiometric coefficient. And all we've done is just taken this equation and we've selected 2 parts from it that we want. One of them is what we already know, the moles of NH3, which is 2.3 moles, and the other is the one we want to know, the moles of H2O, again divided by the stoichiometric coefficient. And now it's a very simple matter of multiplying both sides by the denominator of the reactant that you want to find, in this case H2O. So you multiply both sides by 3, this goes up here, so you get 3 times number of moles of NH3 divided by 2, or you can write this as 3/2 times the number of moles of NH3. And once you get used to this, used to thinking about the number of moles of reaction, used to understanding that the coefficients get divided, so N and 2 is 1, this is pretty intuitive. Each reaction has 1 and 2 produced, so it's just divided by 1. Each reaction uses 2, so it's the number of reactions is half. Once you get used to this idea of thinking about it in terms of the number of moles of reaction, you will be able to understand why this shortcut works. And it's more of an understanding based approach than a memorization approach, and it works very efficiently and it allows you to get to the answer very fast. So if you want to find the number of moles of H2O and you're given that there's 2.3 moles of NH3, as was the case in the previous problem as well, then you simply need to multiply the number of moles of NH3 by 3/2. So 2.3 times 3 divided by 2, 3.45, exactly the same as we got previously. That's because if you don't have to find the limiting or excess reagent, you can just skip the finding the number of moles of reaction part and just write this equation out and take the parts which are necessary and rearrange to solve very simply for the moles of any reactant or product. Hopefully this will save you a lot of time, and hopefully it'll give you an intuitive understanding and appreciation of why stoichiometry works the way it does. I hope you found this video useful, and have a great day. For the making of this video, I used a reaction which I found in my higher level chemistry textbook, which is by Pearson, written by Catherine Brown and Mike Ford. And I looked at the reaction on page 30, and so I'd like to thank them. I used CodeCogs to create this equation. CodeCogs is really nice. It allows you to edit equations much better than Google Docs or even MS Word. And so I would really recommend them, and I thank them. And Sketch.io was the program on which I did this. It allows you to draw and stuff. It's really nice. So I just like to give credits to them, and thanks. Thank you for watching as well. Goodbye.